Hi, chemistry class. Today, my explanations will be fairly short because this topic, ice tables, is super important before we move on. So I just want to take today to make sure everybody gets good at this. Okay? So we use ice tables to apply stoic to chemical systems that aren't quantitative. Remember, quantitative is a reaction that's 100% yield, so it can't go backwards. But we are much more interested in equilibrium systems, that is the name of the unit. So we're going to deal with systems that aren't quantitative. And today we see how do we apply stoichiometry to that. Okay, so I'm going to bring back our familiar example. But first I've kind of used cool font here, big letters. ICE stands for initial change equilibrium. All right. So here's the familiar example. I got ahead of myself. 2 moles of hydrogen with 2 moles of iodine, and then I'm telling you at equilibrium we're going to get this much hydrogen iodide. Okay, we're going to use an ice table to determine how much hydrogen and iodine are left at equilibrium. Okay, so let me show you what that looks like. To set up a table, write your reaction. Okay, so there's my balanced reaction. The I stands for initial. You can use ice tables for amounts or concentrations. We'll do it at a concentration amount later. This is going to be an amount example. So we start with 2 moles of these two guys. They're put in a container. None of this exists before the reaction starts. But we were told that 3.1 moles of hydrogen iodide are present at equilibrium. Okay, so this is just the table set up with what we're given, and I'll show you how to fill in the rest. Okay, we know the initial amount of hydrogen iodide and the equilibrium amount. That's going to tell us a change. Just subtract. Don't like that pen. Okay. You apply the stoic ratio to the change row. Okay, so that's where the stoic comes in. 3.1 was the change in hydrogen iodide. That's what you multiply by the stoic ratio to find these guys' change. So to find iodine, it's 3.1 times desired over given, which would be 1 over 2. So I'm going to write that. Okay. That's going to be 1.55. I think you'll agree hydrogen's going to have the same change. It's got the same coefficient as iodine. Now the next thing we just have to worry about is the reactants, things on the left of the system. The change is going to be negative because they're reacting. Okay? And this is always true. Everything on the left of the arrows goes down. Everything on the right of the arrows goes up. To find the equilibrium amounts, you just do initial with the change. So 2 minus 1.55, that tells us 0.45 moles. Same with iodine. Okay. I'll write little moles here because that's what I was asked to do. That's how we use an ice table. I'll do another example.